Okay, so we're moving on to 17.2, which is all about buffers. And that may be a concept that you may have heard something about, especially if you took AP Bio. The idea behind buffers is that they are composed of a weak acid and its conjugate base, so a solution of two things. And the purpose of a buffer is that it resists changes in pH when an acid or base is added. In our body, there's a biological system of buffers so that the pH of our blood stays approximately the same, no matter if there is some acid that's added to the blood or there's some base that's added to the blood. We know that carbon dioxide will react with water and form carbonic acid, and so that's part of the buffering system that the body uses. The strategy for approaching this is really the same as the common ion effect, because what we're talking about is a weak acid and its conjugate base, which was exactly the idea of a common ion. So if you think about, this could be any system, but this would be hydrofluoric acid and its conjugate base. So let's say we added some sodium fluoride to it or some potassium fluoride, so that we have the concentration of these two compounds is about the same. And we can figure out what that pH is. That's what we did in the last section. Here's why this is a buffered system. Because if I added some acid, what would happen is the conjugate base would react with the acid, because bases react with acids, and it would produce a little bit more of that conjugate acid, of the weak acid, HF. You can see that, like, yes, do the amounts of HF and F minus change? They do, but not significantly. The same thing would happen if I added some base. Of course, what would the base react with? Well, the base would react with the acid, and it would produce, we would see the conjugate base would go up a little bit and the acid would go down. But this is really in great contrast to what would happen if you just added an acid to a non-buffered system. And we'll do some practice with those. So the first type of question is just, what is the pH of the buffer? What is the pH of a buffer? That is 0.12 molar lactic acid and 0.1 molar sodium lactate. And then it gives us the Ka. So of course, we are going to need to find the H3O plus concentration. And we can put that in an ice chart. So I'm not going to write out the whole thing for lactic acid. I have a weak acid plus water in equilibrium with H3O plus and its conjugate base. And the question says that I'm starting with 0.12 molarity lactic acid and 0.10 molarity sodium lactate. And water we don't care about, and H3O plus would start out as 0. And we've done this a bunch of times. Both of these would go up by X and down by X. And because we know it's a weak acid, we can call that negligible. So now we have our Ka, which was equal to 1.4 times 10 to the negative 4 is equal to the concentration of the H3O plus, which is X, times the concentration of A minus 0.10 over the concentration of the weak acid 0.12. I solve for X. X is equal to, of course, the concentration of the H3O plus, and that is the concentration of the H3O plus is 1.68 times 10 to the negative 4, and the negative log of that, so the pH is equal to 3.77. So now I know that the pH of this buffer is about 3.77. If I add a little bit of acid, it will change a little. If I add a little base, it will change a little, but it'll stay right around 3.77. Now there's another way that we can solve buffer problems, and that's with something that's called the Henderson-Hasselback equation. And this is one of the equations that's on your equation sheet. And it's sort of a shortcut because, as you've noticed, some of these we seem to be doing the same thing over and over and over again. So this is a formula that sort of has done that already. And it's pretty straightforward. What is the pH of this buffer system? Well, what is the pKa? So I would take the negative log of the Ka, and that's 3.85. And then I would add that to the log of the HA, which is my conjugate base, which was that 0.10. And the acid that we started out with was 0.12. And literally you just plug this into your calculator, and this is a lot less work, as you're going to see. It comes out to be 3.77. It's really like the ice chart, because that has been done so many times. Like the pattern is basically like that's done for you. How many moles of ammonium chloride must be added to 2 liters of 0.10 molar ammonia to form a buffer whose pH is 9? So the first thing that I'm noticing is this is not a weak acid system anymore. This is a weak base. So things are going to be a little bit different, but honestly not much. We have the balanced chemical equation, and we can write an ice chart for this. So the balanced chemical equation would be the ammonia reacting with water, right? It's a base, so it would grab a hydrogen off of water to make NH4 plus and leave behind OH minus. What am I starting with? Well, I'm starting with the fact that we would have 0.10 molarity ammonia. I don't know how much ammonium chloride I would start out with. So this is sort of my, I don't know. The OH minus, I would start out with 0. And the ammonia would go down by some amount, and the ammonia might go up by some amount, and the OH minus might go up by some amount. And then what would be the equilibrium row? Well, again, it's weak, so this X is negligible unless you're comparing it to 0. This is going to still be the one I'm looking for, right? The question was asking for moles of ammonium chloride. And this guy, how would I know this guy? Well, it tells me that I want the pH to be 9. If the pH is 9, that means the pOH is 5, and so the OH minus concentration is 10 to the negative 5. So use the Kb to solve for the equilibrium row, right? The Kb for ammonia is 1.8 times 10 to negative 5. That's equal to that unknown concentration of ammonium times 10 to negative 5 over 0.10. I solve for that unknown. It is the concentration of the ammonium ion, and that is 0.18 molarity. The question actually, if you look back, the question actually asks how many moles, and it says per 2 liters of solution, right? So if we know that molarity equals moles over liters, the molarity is 0.18. I don't know the moles, but I know the liters is 2.0. Then I could just multiply those two numbers, and that will give me that it's 0.36 moles of ammonium chloride, NH4Cl. As always, you can use the Henderson-Hasselback equation for this. Henderson-Hasselback isn't just used for calculating pH. You can calculate, there's 4 different variables in there, and as long as you have 3, you can calculate for the 4th. So if we look at, right, there's the Henderson-Hasselback equation. What do I want the pH to be? 9.0. What's the pKa? So how am I going to get, you might want to do negative log of 1.8 times 10 to negative 4. Remember that if you do that, right, we know that the Kb is 1.8 times 10, I think I said 4. It's 1.8 times 10 to negative 5. So that means this, if I take the negative log of that, I'll get the pKb, and that's 4.74. So in order to get the pKa, 14 minus that. Right? So the pKa is equal to 9.25. And that's plus the log, right? A minus, when we think about what that is, that's the conjugate base. You can think of it as just like that. This is just the base. And this guy is the acid. It could be the acid and its conjugate base, or the base and its conjugate acid. But it's the base on top and the acid on the bottom. So in this case, I know the base concentration. That's 0.10. And what I want to find out is that number X, okay? So how do I solve for that? Okay, so all we need to do is solve this problem, but this is solving a problem with logs. So the first thing we want to do is we want to isolate the term with the logs all by itself. So subtract 9.25 from both sides. And that will give me a negative 0.25. You know, there's more digits to this. I'm just not writing them all down. Is equal to the log of 0.10 over x. And how you can think about taking 10 to the both sides, or just taking this from a log form into exponent form. And basically when you do that, you will get, or how I did that is I do 10 to the negative 0.25 equals, or 10 to the log of 0.10 over x. And when I do that on both sides, the log, the 10 to that, and the log sort of cancel each other out. So I get on this side 0.55 equals 0.10 over the concentration of that NH4 plus. Cross multiply, and I will get that the concentration of that NH4 plus is equal to 0.18, the same as I got the other way. And of course, same formula, molarity equals moles per liter, 0.18 equals moles over 2.0 liters. And so the number of moles is 0.36. So just two different ways of solving for this. The last topic that we're going to look at in this video is buffer capacity and pH range. Now, you know, what we said was what buffers do is they help keep the pH steady, so that if I add a little bit of acid or if I add a little bit of base, the pH will remain approximately the same. So that means that there's an amount, like there's a little bit is a non-technical term, and we probably could find out exactly what that is. If you hear the word buffer capacity, it's basically the amount of acid or base that can be neutralized before the pH begins to change appreciably. Right, and this is again a little bit arbitrary. What does appreciably mean? Basically, the greater buffering capacity happens when you have greater concentrations of that weak acid and that conjugate base. And the pH range is the range in which the pH the range in which that buffer will be effective. And it's generally thought of as plus or minus 1 pH unit from the pKa. So if you find a weak acid, right, if you take the negative log of its Ka, that will give you its pKa. So that means we can make a buffer that is somewhere, you know, that will keep it within 1 pH unit of that. So how do you choose the right acid base to make a buffer solution? You want to look at the pKa and find the pKa that matches your target pH. And that's what this question is. The Ka value of nitrous acid and hypochlorous acid are given there. Which would be more suitable for using a solution buffered at pH 7? What other substances will be needed to make this buffer, even without a calculator, right? I know that, this is why we teach you this, that the negative log of 3.0 times 10 to the negative 8 is 7 point something. The negative log of 4.5 times 10 to the negative 4 is 3 point something. So this is not going to be useful if you need a buffer to keep it around pH of 7. So I know I'm going to be using that second acid, which was the hypochlorous acid. So the first question, which one would be more suitable? That would of course be the HClO, the hypochlorous acid. And what other substance would be needed to make the buffer? Well, I would need something that would have its conjugate base. So some ionic compound that had as an ion the hypochlorite ion. So maybe sodium hypochlorite, or potassium hypochlorite. Just any ionic compound that when hits water will increase that ClO negative concentration.